Most solar systems start out with a composition that is roughly 73% hydrogen, 25% helium, and 2% everything that's anything else. Okay, so almost entirely hydrogen and helium. Those were given to us during the Big Bang, and everything else was fused inside stars. When we look at our solar system and the kind of objects that we see at various distances, we see some familiar patterns. We have the rocky, metal-rich planets, which we call the terrestrial planets, which are closer to the sun. Then there's an asteroid belt, a tenuous belt of rocky debris. Next, you have what we call the Jovian planets, or the gas giants and ice giants. And then outside of that, we have a lot of ice dwarfs, which occupy a region called the Kuiper belt and the scattered disk. That population of icy objects, cometary stuff, kind of extends out in a spherical shell. That region, that spherical shell, is called the Oort cloud. So now let's take a look at the solar system inventory. And the first thing that you see here is, of the solar system, of all the gas and dust and planets and moons and everything that's orbiting the sun is 99.86% of all of it, right? So almost everything is the sun. We can see a little pie graph here. Almost everything else is Jupiter and Saturn. So let's take a zoom into that little pie piece, and we see that of that, nearly 3/4 of what remains, 0.01% of the solar system is Jupiter. Saturn's a small portion, and then that tiny little wedge up at the top represents the rocky, metallic, icy, solid bodies in our solar system. So if we take a look at that, we see that Earth is about half of all the rocky, icy planets and moons in our solar system. A close second is our twin, Venus, which is roughly 85% of the mass of the Earth. And then if we look at the pie piece that is moons and dwarf planets, Earth's moon is most of that, right? So roughly 2/3 of what remains is in our moon. And if we break this down and look at the asteroids, you see asteroids represent roughly this tiny blue pie slice there. Ceres represents the biggest fraction of that. In terms of mass of our solar system compared to even Earth's moon. So when I said a tenuous asteroid belt, I really mean it's pretty tenuous, not a whole lot of stuff there. Okay, so if we look at some of the observations that tell us how our solar system formed, one of the key observations is when we look at the orbits of the planets, they're all orbiting in the same direction around the sun, nearly in the same plane, with exceptions like Pluto, which is inclined by about 17 degrees. Most of them are nearly the same plane, and that the direction that they're orbiting happens to be the same direction that the sun is rotating, and it's the direction that most, but not all, of the planets are also rotating. Okay, so they're also mostly on very nearly circular orbits. All right, and then we notice compositions depend on the distance from the sun. So closest to the sun, we have what we call the terrestrial planets. These are rocky and metal rich. Then we have the asteroids, rocky debris between Mars and Jupiter's orbits. Then we have the Jovians, which planetary scientists often talk about as the gas giants, Jupiter and Saturn, and the ice giants, Neptune and Uranus. And then finally, the furthest stuff that we see is pretty icy composition, things like Pluto and comets. So the theory that we use to describe the formation of our solar system is called the nebular theory, and it was originally Pierre Simon Laplace in the 18th century. The story goes that a solar system formed from a collapsing molecular cloud, with the sun forming at the center and the planets forming from a debris disk that surrounded the newly forming sun. So first there was a collapse phase. You could imagine a clump of gas and dust that's somehow jostled around. The usual idea is a shock wave from a nearby supernova, explosion of a massive star, some sort of turbulence in the gas causes it to begin to collapse gravitationally, right? And the motion of that gas is turbulent. Still, even with all that turbulence in the gas, there is still some direction of total spinningness of the material. We call that angular momentum. And in our universe, for an isolated system of stuff, the angular momentum is conserved. So as this material begins to collapse gravitationally, collisions heat it up. There are more collisions where the material is densest, closest to the center, so it's hottest in the middle and coolest as you move further out. And collisions also tend to flatten the disk. Because of the conservation of angular momentum, the disk remains extended in a plane, right? So we start with a three-dimensional cloud. It collapses gravitationally, but only into a plane, not into a sphere, not into a ball. And when we have collisions, tend to circularize their orbits and keep them in a plane. So what you're left with is a roughly, two-dimensional plane with some thickness, hottest in the center and coolest as you move further away, with the sun forming at the center of the disk. And we see this. We see this all over the place. So this is a stellar nursery, the brightest nebula in the night sky, the Orion Nebula, as seen from the Hubble Space Telescope. And if we zoom in on some of these spots, you can see newly forming stars. This one might be my favorite because you can see the star just peering through this very opaque cloud of dust and gas, which is in the shape of a ring, like Saturn's rings. And in the inset here, I have another one where we're seeing the disk sort of edge on, and you can see that the disk it's got some thickness to it, and it flares out on the edges. We also see this from microwave observations. All of these are protoplanetary disks seen from the Atacama Large Millimeter Array in Chile. And we can see a lot of structure in these things. We can see the brightness tells us something, the brightness and the color tells us something about the temperature. So we see that they're hottest in the center, and they get cooler as you move further away, but you also see a number of gaps, spiral arms, things like that. And all of those are created by planets, which are okay, so here's just another one of those, and you can see that I've got an arrow on here which is showing the temperature gradient, and the temperature drops off as we move away from the center in the disk. Well, eventually, you reach a point where the temperature is low enough for ices to condense. Okay, so what do I mean by ices? I mean things like water, H2O, methane, CH4, and ammonia, NH3. those things will condense into ices, but only where the temperature is low enough for that to happen. And we call that line from the center of the solar system, that's circle, the snow line. Inside of the snow line, all those things are gases. And outside of the snow line, they are solids. They condense into small solids. We also could talk about a rock metal condensation line. If you get close enough to the center of the disk, the temperatures are thousands of degrees, and even rock will be in a vapor form. But once we move outside, just it cools off enough, just below 1,000 degrees, you start getting solid bits of rock and metal condense out. So you start out, everything's in a gas form, close to the sun. As you move away, you get little bits of rock and metal. As you move further away, you have little bits of rock and metal, but also little bits of ices. So there's just more solid stuff as you move further away from the newly forming sun in the protoplanetary disk. Okay, now what happens to these snowflakes? Well, we got to turn them into snowballs. Called the van der Waals force. Will, through collisions, they'll start to collide and stick together, and they'll go from very, very tiny grains up to centimeter scale pebbles. All right? And now we have to imagine how those pebbles are orbiting within this gas disk. So we still have a lot of gas surrounding them. And one of the things that I teach in my astronomy class is that the orbital speed is proportional to the square root of the central force. And this is a familiar example from what's called Kepler's third law of planetary motion. And if you're not familiar with the mathematics of it, the gist of it is that things that are further from the sun orbit slower than things that are closer. So Mercury orbits with a faster orbital speed than Saturn merely because it's closer to the sun. But now we have gas and we have pebbles. And the gas has the force of the sun's gravity pulling in, but there's also a pressure gradient where the gas is denser, closer to the sun, is pushing on the gas to where the gas is not less dense, which is away from the sun. So you have this gas pressure force. And we consider these two forces that are opposing each other. The force that's keeping the gas in a circular orbit is a little bit smaller. And therefore, the gas in the disk orbits just a little bit slower than these rocky pebbles do. And so what's the point of all this? The point is to say that those is acting like a headwind, pushing back on them, trying to slow them down. And in the process of slowing them down, they want to fall inward closer to the sun. So this brings us to our first fundamental problem in understanding how the planets form, which is called the meter size barrier. So gas drag causes everything to migrate towards the sun, to spiral inward. And the migration is fastest for objects that experience the most gas drag based on their mass, which is about 1 meter sized boulders. And you can calculate how long it takes for a 1 meter sized boulder to go from a distance of Earth's orbit around the sun and to spiral into the sun, and it's only about 100,000 years. So that's short on the scale of the solar system. We know that the solar system is about 4.5 billion years old, and we know that the formation of the planets happened with over something like a 25 million year time scale. This is short. So how could they have possibly formed so fast that they didn't migrate into the sun? One of the solutions to that is what's called pebble accretion. And this happens when there's sort of instability between the drag and the particles. And I'd like to talk about race cars here. And imagine with race cars, there's a term called drafting, where if you've got a car in the front, they're can go just as fast without being full throttle on their gas pedal because they're experiencing less gas drag. Okay, so the brunt of the force is on the particle in the front. And here's a nice simulation from Nesvarny et al. I can't read my thing here, 2018, I think it is. And we can see how what happens is these tend to form in filaments because the front particle feels a lot of gas drag, and then the particles that are behind it don't feel the gas drag, and they run up into it and collide and stick. So you can form large objects very quickly as long as they're kind of in filaments, so the majority of those pebbles are missing the gas drag because they're shielded from the object in the front. This is one way to generate big planetesimals. And when I say big planetesimals, I mean on the scale of kilometers. Okay, so we make kilometer-sized planetesimals quickly, and then we go into the regime of what's called oligarchic growth. And this is a sort of a random process, but basically you have a few objects, a few larger objects. Because they're larger, they have a little bit more gravity. When they collide with something else, that other thing tends to stick to them, which makes them a little bit bigger still. And you go from having a few million kilometer-sized objects to having just one large object within that area. So we went from having many billions of small planetesimals to having, say, 4 terrestrial planets. Okay, and through oligarchic growth. So then you might be asking, well, what about the gas giants? Why are they so different? How did they form? Well, remember that these formed outside of the snow line. They're further from the sun, and there was just more solid stuff out there. There wasn't just the rock and metal. There was also pebbles made out of water ice. So you get bigger planetesimals. And while the biggest planet that formed inside the frost line is the Earth, the masses of the cores of the giant planets got up to about 10 times the mass of the Earth. And if you know anything about our atmosphere is primarily nitrogen and oxygen, and those are heavier elements. What about things like hydrogen and helium? Well, they just escape. They are too light for a planet like the Earth to hold on to for a significant amount of time. Not true if you have an object that's 10 times the mass of the Earth. So these larger planetesimals, which are larger just because there's more stuff outside the snow line, start grabbing the hydrogen and helium gas that's surrounding them. Okay? From that gas that's sort of swirling around, they form their own circumplanetary gas disks. You have the whole process in miniature, and you have lots of small moons forming in circular orbits around the Jovian planets. And we see this too. So here's another one of these amazing ALMA images, which shows a protoplanetary disk which you can see. And then what's kind of hard to see, but is definitely there, is a brighter patch around that planet, which is the circumplanetary disk that will go and form moons for this Jovian planet orbiting a newly forming star. Okay, so the time scale, how long do these things have to pull on gas and stuff like that? You have to get enough gas before the disk disperses. And what's going to cause the disk to disperse? I'm going to talk about this later, but it's once the sun reaches a state of equilibrium, the solar wind and radiation from the sun will push that gas out of the way. So it'll remove the gas from our solar system. Okay, so there's two types of planet migration, and I want to move into talking about how planets move over millions of years or hundreds of thousands to millions of years in our solar system. And actually, for this part, we're going to talk about migration within a gas disk, which is on the order of thousands of years, tens of thousands to hundreds of thousands of years. And the first way to do that is called type 1 migration. And this happens for any kind of planets or planetesimals that are less massive than Neptune. Here's a simulation, and I'll show you what happens. So this is happening relatively quickly, and the difference in forces from the inside of the disk to the outside of the disk pulls on the planet, causes it to lose angular momentum. It transfers that spinning. Notice that there's no gap opened up around the planet. It's just interacting directly with the disk. But another thing that can happen is called type 2 migration. Type 2 migration happens for bigger planets, something that's as large as Jupiter, for example. And in this case, I'll explain the physics of it in just the next slide. But what happens is the planet is big enough to clear a gap in the disk itself. So there's a clear empty space surrounding the planet, and because of that, the forces from the gas disk on the planet are smaller. The disk is further away from the planet, and the migration still happens, but it happens at a much slower rate. So planets undergoing type 2 migration take 100,000 to 1,000,000 years to spiral into the sun from, say, Earth's orbital distance, where a planet Neptune size undergoing type 1 migration would happen 10 times faster. Okay. So weird thing here, I basically just told you that gravity is repulsive. And if you remember, your high school physics or something like that, I thought gravity pulled all masses together. How can gravity cause a planet to open a disk? And I like to give an example of Saturn's moon Pan in the Encke gap of Saturn's A ring. And the way I like to talk about it is this. Remember that everything here is orbiting Saturn, which is over on this side, over here. And so the stuff that's closest to Saturn is orbiting faster than stuff that is further from Saturn. So everything's orbiting. And the moon has some significant amount of gravity compared to the ring particles. Well, let's just draw a circle around the moon where influence becomes dominant. It becomes really important to the ring particles compared to the central body of Saturn. Okay, so now what happens to these ring particles over here? They're streaming by and they're moving faster than the moon. Okay, they're moving faster than the moon. They whiz past the moon, but now the moon is saying, hey, slow down. I'm tugging you back and pulling on you with my gravity. And as they slow down, they still pass the moon, but they fall closer to Saturn. Now, what about the moons on the ring particles on the outside over here? Well, the moon is rushing along faster than they are. These ring particles are coming by the moon from this direction, and la la la. Okay, and then they're going slower than the moon, but the moon says, "Wait a second, I'm bringing you along for the ride." It pulls them from the front and speeds them up. And when the moon speeds the ring particles up, they gain angular momentum and they move away from Saturn. So this is the same process in a protoplanetary disk. The moon opens up a gap, because of its gravitational influence. A planet can open a gap because of its gravitational influence. And one of the things that is kind of interesting in this picture, there's two moons like this. There's Pan here. There's also Daphnis over here. And you can see the wakes that they produce, just like wakes from a boat, but unlike wakes from a boat, which are behind the boat on both sides. Behind it on the outside. Same goes here, right? And that's because of the different orbital speeds of the different objects. Okay. Another thing that you can see that in this picture, which I think is important to mention, is resonances. And so there are places where just by the positions that they're at compared to different moons, ring particles will go around, say, for example, 5 times for every 4 times the moon way out here, Janus, goes around. That creates what's called an orbital resonance. And one of the things that's nifty about Saturn's rings is where you have these orbital resonances, they trigger what are called spiral density waves. So these are very tightly wound up spiral waves, but the physics is exactly the same as spiral arms in galaxies, which trigger star formation, and spiral arms in protoplanetary disks, like seen here from one of those ALMA images. These spiral arms are indicative of a planet that's resonating with that gas and creating this 2-armed spiral, right? For this one, for example, though, we'd have a 5-armed spiral, right? So they're different amount of arms depending on the resonance. Okay, so let me try and simplify this resonance idea a little bit more. Here's an animation that shows Jupiter's moons, Io, Europa, and Ganymede. We've left out Callisto. Callisto is the other large moon of Jupiter, but it is not in a resonance. And what we see here is that in this, what's called a Laplace resonance between found 1/2 of an orbit, and Ganymede goes around 1/4 of an orbit. So these are locked into a resonance. What that means is they tend to line up periodically, which means that the gravitational pulls from these small objects can add up over time. Instead of averaging out to 0 by pointing in lots of different directions, little tugs start to swing the moon, start to swing the system, and can pull it out of its particular orbit, or can cause it to want to rest in a particular orbit. I like to think about this as pushing a child on a swing, right? It's pretty hard to lift the child all the way up as high as you want them to go, but just by pushing at the natural frequency of the swing, little pushes can add up to a big motion, right? Another example of a resonance is Pluto and Neptune, which are in a 3-to-2 resonance. So Pluto goes around the sun twice for every 3 times Neptune goes around the sun. Because of that, even though their orbits cross, Pluto and Neptune will never collide. They will never be at the same position at the same time because of their resonance. So then the other question is, what about this asteroid belt? Who ordered that? Why didn't it just form another planet that's small, but why didn't it form one? And the answer is resonances from Jupiter. This was noticed first in the 1800s by Kirkwood. They're called trapped in particular positions because of their resonance with Jupiter. So, for example, right here we see what's called the Hildas. They orbit 3 times for every 2 times Jupiter goes around. Or if you have a large population of asteroids, then these things, their orbits become more and more stretched out, more eccentric over time, and they can collide with other objects, and you end up with a paucity of asteroids at certain locations, like here, for example, where the asteroids would go around 3 times for every 1 time Jupiter goes around. Okay, and keep in mind, the strongest resonances are the ones that have low numbers. And that's because this is a sinking effect, like pushing on a swing. If you're pushing a child on a swing and you skipped every 4th push, it would take a lot longer to get the child swinging, right? So same effect here. If it's a low order resonance, you're getting a lot of pushes relatively quickly, and then you get a big effect. So another thing that we see are what's called, and we look out at exoplanetary systems, planets orbiting other stars, we see hot Jupiters everywhere. We understand the mechanism by which Jupiters form. They're big, they're gaseous, they have to form outside the frost line. Otherwise, they wouldn't be massive enough to hold on to that hydrogen and helium gas. But when we look out at a lot of exoplanetary systems, we see things the size of Jupiter that are orbiting much, much closer than Mercury in our solar system. Solar system. We also see planets. The TRAPPIST-1 system is a really cool one. It's got something like 7 Earth-sized planets, 3 of which are in the zone where liquid water could exist around this star. But all of them are in a resonant chain. So in other words, they're in resonance with each other. Somehow they got trapped at these particular distances from their star. This also suggests migration. Okay, so now I'm going to talk about a really fun idea from the early aughts called the Grand Tack hypothesis. And we're going to start back when the solar system was just forming. There was a protoplanetary disk, and Jupiter formed first. It formed first, and it was in the most densest part of the disk, so it got big. Then you had Saturn form. Saturn didn't get quite as big as Jupiter. And what happened is, as they were forming, Jupiter started to open up a gap in its orbit. It was going through what we call type 2 migration. At the same time, Saturn which formed further out, was undergoing type 1 migration, which is faster than type 2 migration. So Saturn was moving inward, Jupiter was moving inward, but Saturn's moving inward faster. It's catching up to Jupiter. Then what happens? Then Saturn gets to the position where it orbits exactly once for every 2 times Jupiter goes around, and they find themselves in this orbital resonance. That's pushing on Jupiter. I'm sorry, on a sailboat tacking into the wind. Jupiter gets pulled back out. We think that Jupiter made it in as far as Mars's orbit into the inner solar system before turning around. And this explains why Mars is so small. Mars being further where in the region of the disk where temperatures are a little bit cooler, you'd expect more rock and metal in Mars than there would have been where Earth formed, and you'd expect Mars to be bigger. But there, for some reason, was less material where Mars formed than where Earth formed. And that we think that's because of Jupiter's Grand Tack. So then what happens? The sun becomes a true star. This happens about 25 million years after it begins to form. It was very, very active. It spun a lot faster than it does now, which is about once on its axis every 25 days, at least at the equator. And it had very strong magnetic fields, which kind of coupled to the gas in the disk. This is ionized gas. Electric charges end up feeling those magnetic fields. And this slowed the sun's rotation down. But at the same time, it sped up the gas in the disk, and that stuff was also pushed away by solar wind. Solar wind is a bunch of charged particles, mostly protons and helium nuclei and electrons that are always leaving the sun. And that pushed out or dissipated or evaporated the gas disk. That's what ends the growth of the Jovian planets like Jupiter, Saturn, Uranus, and Neptune. Around. There's all these planets, and for this portion of the talk, I only want to talk about the biggest ones, which are Jupiter, Saturn, Uranus, and Neptune. We'll neglect the terrestrial planets; they're too small to care about. But there's a bunch of debris. There's a whole bunch of cometary debris that just never had time to form planets. And Hal Levinston and company over in the Observatoire Côte d'Azur in Nice, France, put out a series of papers in the mid 2000s with which is now called the Nice model. And basically, the idea is, how can you get the planets to move around? Well, they can throw baseballs back and forth. Right? So you can transfer momentum or transfer forces by throwing baseballs back and forth. You can imagine two kids sitting on skateboards, throwing a basketball back and forth. And if you throw a basketball, then you start moving backwards. You catch a basketball, you start moving backwards. Conservation of momentum, allows you to transfer forces through throwing these things. So what happens now? Jupiter is sort of playing baseball with the outer planets. It tosses a comet in Jupiter's orbit outward, and then either Uranus or Neptune can toss it back inward through a close gravitational encounter, or they might toss it out of the solar system. And this has the effect over many, many of these close gravitational encounters with comets of the planets. So remember, Jupiter and Saturn migrated. They cross this 2-to-1 resonance, and absolute mayhem happens. I misspoke here. Let me say this again. Jupiter and Saturn are both migrating outward as they throw comets into the inner solar system. And eventually, Jupiter and Saturn again cross the 2-to-1 resonance with each other. And this is absolute chaos. Everything starts getting tossed in and out of the solar system. Interesting thing happens is Uranus and Neptune move much further out, but they also swap places. So Neptune formed closer to the sun, but now it's further out than Uranus is. And this period of time, this mayhem that I'm talking about, is what we call late heavy bombardment. So it's about 3.85 billion years ago. Just about 700 million years after the origin of the solar system. No longer is there a gas disk, but there's all these leftovers from the accretion process. This is the origin of the large impacts on the moon, the lunar mare. Earth, Venus, Mercury, Mars were all impacted a lot during this time. We don't see those craters on Earth because Earth has erosion and plate tectonics, which tend to erase craters. But we see a bump in the number of craters right around this time because of the Jupiter and Saturn throwing around all these comets. This is also all that icy debris would take too long to form if it formed in place. Instead, it formed closer to the sun, closer to the snow line, and was tossed out during this scattering event from Jupiter and Saturn. This also explains the origin of the Oort cloud. right? So all these comets that were tossed back and forth by the large planets, some of them were tossed way out of the solar system, orbits at 1,000 times the average distance from the Earth to the Sun, all the way out to 2 light years, about halfway to the nearest star. And so those long period comets are also from that Nice model process. Okay, so let's pull it back in. Evidence from meteorites. This is what we call a carbonaceous chondrite. Some of the first things that we see in our solar system. This is completely unmodified since it originally formed. You can see the individual pieces that made up this meteorite. And some of those individual pieces are called calcium aluminum inclusions, or CAIs, and others are called chondrules. Chondrules are relatively millimeter-sized spheres of material that cooled off rapidly. So these are droplets, essentially, droplets of rock and metal that condensed from that original solar nebula. When we radiometrically date these things, we look at the fraction of, for example, aluminum 26 to magnesium 26, or potassium 40 to argon 40. We can very accurately determine the date at which they became old, these carbonaceous chondrites. We also have some really cool objects, Jupiter's Trojans, which have been kind of stuck in the same orbit as Jupiter, but 60 degrees in front of and behind it at what are called Lagrange points. These are also a little bit of a time capsule. So these are those objects that Jupiter and Saturn were tossing around. Some of them ended up getting trapped in Jupiter's orbit. And NASA's Lucy mission, which is led by one of the Nice model progenitors, Hal Levinson, is on its way out there to go observe 5 asteroids on either side of Jupiter's orbit. That's in the next coming years. This is its trajectory. So it's going to have to fly across the solar system to go see these different asteroids. And then, of course, we've got these comets and icy bodies. There's Jupiter family comets that are in Jupiter's orbit. There's short period comets which originate in the Kuiper belt. And there's long period comets which originate from the Oort cloud. Halley's Comet, for example, is a Kuiper belt object. It's a short period object, period of like 75 years. That's what we call short period. Long period would be something that has a orbital period of 10,000 or maybe 100,000 years. And what's cool about studying comets is they preserve the early solar nebula volatiles. So the gases and stuff like that are frozen out on comets. When we observe them, we're seeing what the protoplanetary. But of course, there's some exceptions, right? Things that we didn't talk about and our model doesn't explain, our nebular theory doesn't explain, are some of the weird axis tilts of the planets. Uranus is tilted on its side, so its axis tilt is like 98 degrees. Venus rotates backwards very slowly. Its axis is tilted completely upside down, 180 degrees almost. And then Earth is the only terrestrial planet with a very large moon. That's also kind of weird. And so how do astronomers, planetary scientists explain these types of things? Impacts. When astronomers get lazy, we say impacts. It's all from impacts. For example, Earth's moon was likely created when a Mars-sized planetesimal barreled into the Earth, gouged out a large section of its mantle and crust, and that material coalesced to form the moon. Same could be said for Uranus's axis tilt, 2 times Earth-sized impactor, and also for Venus's axis tilt. We also have all of our moons. The large moons in our solar system are predominantly around the gas giants. these regular satellites formed from circumplanetary disks. They also show orbital resonances, tidal heating, so they get hot from tides over their orbital period, and also migration. We see the moons migrating. Then there's irregular satellites. Those are mostly captured objects, things like the irregular moon Phoebe, which orbits backwards around Saturn. Most likely, this was a captured asteroid. Particularly odd pair. Mars' moons Phobos and Deimos are fear and dread. Here's some pictures of them, and here's a picture of Phobos in front of Mars. Often astronomers tend to bring up the brightness of objects so we can see all the features on them, but most of these small moons, just like asteroids and comets, are particularly dark. Most comets and asteroids are about as dark as charcoal. And when you look at Phobos in front of Mars, orange Mars, you can really see how dark it is. The lighting is from the same direction, right? And so when we look at the colors and the compositions of Phobos and Deimos, they really seem like captured asteroids. But they're orbiting around Mars's equator. They're orbiting in the same direction as Mars is rotating. And one of them is migrating outward while the other one's migrating inward and will eventually form rings around Mars. And for those reasons, it seems like a crazy coincidence for them to end up in that kind of configuration and to have been captured. So the jury's still out on whether Phobos and Deimos were captured asteroids or whether they formed around Mars. Is our solar system unique, and is it stable? It's definitely not what we see in other systems. We see lots of hot Jupiters. We see super Earths. Super Earths are things with 2 to 5 times the mass of Earth, sometimes in chains of many super Earths. Is this observational bias because it's easy to find things that are closer to the star and orbit faster, or not, or are we just unique? There's motion that stirs up the planet's positions on the scale of hundreds of millions of years, but it is not so chaotic that it's just going to throw out a planet or something like that. It's metastable. The stability is affected by resonances primarily between Mercury, Earth, and Mars. So let me go back and tell you what we covered. The solar system collapsed from a nebula. We see evidence for this elsewhere in the universe, in our galaxy. Protoplanetary gas disks are a complicated place. Forming planets without them spiraling into the sun is hard. Heavyweights like Jupiter and Saturn tossed planetesimals around the solar system, slowly exchanging momentum with each other and other planets. And resonances make weak gravitational forces add up over millions of orbits. When astronomers get lazy, we explain things with impacts. And so how about some unanswered questions? How did planets form from dust? We have the meteor barrier. Why is it that planets were able to form quickly enough to not migrate into the sun? Why are exoplanet systems so different from our solar system? Is our solar system unique? And what triggered the Nice model instability? Why at that particular time? Could it have happened at any time? Has it happened at other times? Uranus's rotation. Do we think that impacts happened a lot on Jupiter and Saturn? Maybe so. Evidence is starting to lead us in that direction. And that's all I have for today. So thank you very much for having me. I was excited to be here, and I'll take any questions if you have them.
Thank you, Dr. Jerousek. My brain is strained. Questions? Yes, sir.
So the moon, our moon, is receding from Earth at about 4 centimeters a year. Is that explained by some of these phenomena you talked about?
You dropped out for a second. I heard our moon and then
Is
silent.
receding. It's drifting away from the Earth at about 4 centimeters a year.
That's right. Yeah.
So is it?
So that's caused by tides, right? So it's this conservation of angular momentum, and what happens is the Earth. Actually, I can go back and I'll explain it with Mars's moons too, because it's an interesting phenomenon that's similar. So Deimos its orbit is further out than where an object would orbit at the same rate that Mars rotates. And that position is called geosynchronous, or I guess in this case, Mars synchronous. The moon is further away than Earth's synchronous location, which is where an object would orbit at the same speed that Earth rotates on its axis. Well, the moon also pulls on the Earth a bit, and the Earth pull your distance from the object. So you can imagine the Earth kind of being stretched a little bit. Imagine it's stretched into a football shape instead of being perfectly round. And this thing's rotating. But now this football-shaped object has a little bit of a force on the moon over here. And that force tends to pull the moon around in its orbit. Okay? So what happens is the spinning motion of the Earth is slowly being transferred into the orbital motion of the moon, making it slowly drift outward. And so that's what you're seeing here. But at the same time, you're losing the spinning motion of the Earth. So in something like 50 billion years, the Earth will rotate at the same speed that the moon orbits, 1 month, which will be a lot longer than 1 month now because the moon is moving further away. So that'll be something like 50 Earth days. But I think that none of us will be there by that time.
My memory says that at one point the spin of the Earth was in 20 hours.
Right. It was faster. And so the moon has been drifting away all this time, and by drifting away, slowing the spin of the Earth. And so Mars's moon, Deimos, is doing exactly the same thing here. But Phobos is much closer to the Mars. It's orbiting faster than Mars rotates on its axis, so it's moving in the opposite direction. And it's speeding up the planet's rotation. So Phobos is falling in, Deimos is falling out, and it's all because of tides from Mars. Yeah.
I have a question. A gas disk around a star. I believe I remember correctly that you said that outer mass is causing spiral arms to develop within the gas disk. Mass that's outside that spiral arm formation zone is actually causing those spiral arms to develop. Is that
right? So, for example, in the Saturn's rings picture, where did it go? The spiral arms in Saturn's rings and in the gas disk. Mm-hmm. Yeah, I'll find that. So right here.
Yes. And my question simply is, okay, in a spiral galaxy, what is the outer mass?
That's such a good question. And I'm teaching a class in galaxies and cosmology this year, and the mass distribution of stars in our galaxy is not uniform. And it turns out that the Milky Way galaxy has gobbled up quite a few smaller dwarf galaxies in its lifetime. One of them is called the Sagittarius dwarf galaxy. And we can trace back how stars have been ripped apart from this galaxy by tides. We can see some of its outer stars and how they orbit the Milky Way. And we can trace back this overdensity of stars, the Sagittarius dwarf galaxy, which is kind of clumped up in a particular position in the Milky Way's disk. And so we think that these cannibalized galaxies are responsible for the spiral arms in galaxies. Yeah.
Okay. Thank you for this. It's totally fascinating. And equally cool is that you worked on the Cassini project. And I'm just you are continuing to analyze the data. And so I'm wondering what you have discovered in that data that you've analyzed lately.
Right. So there's a bunch of different teams that are doing this work. And what I focus on planetary rings. And the tool that I use the most in studying Saturn's rings and also the Uranian rings are what are called stellar occultations. So as the spacecraft orbited around Saturn, we would stare at a star as it passed behind the rings and traced a line through the rings. We could measure the transparency as the spacecraft orbited by measuring the light through the rings. And so we measured something like 280 9-hour-long stares of staring at a star as it moved through the rings. And that allows us to they're all at different viewing geometries too. So sometimes we would be looking when the rings are nearly edge on. Sometimes they're up like this. And so that allows us to put together something like a computed tomography or a CT scan of the rings. So in a CT scan in a hospital, you have an X-ray device that spins around you and takes measurements of how transparent your body is to the X-rays at various angles. And then the computer puts together a three-dimensional picture of your body. We kind of did the same thing with stars, and we focus on the small scale structure in the rings. So the individual particles clump kind of can't quite do it, so they form football field sized fingers in the rings. We call those self-gravity wakes. And so I think those kind of things are the most interesting things that I've discovered in the rings. Yeah.
So from our Zoom audience, we have a question. Roughly how many similar solar systems have likely formed in the universe? Not just the galaxy, but he wants to know the universe. Or at least were formed by similar processes.
Right. So we have a pretty good idea that the process that I explained is the sole process for forming solar systems. They always form from protoplanetary disks. Now, as far as our solar system goes, we've never found another solar system like our own, where we have a lot of planets, first of all, but a handful, like 4 big ones that are really far away from the sun, from their parent stars. And that might be because it takes a long time to analyze that data. Keep in mind, Saturn takes 30 years to orbit the sun one time. So that's a long time for a grad student to be poring over data to come to a conclusion, right? So yeah, we don't see a lot of other solar systems like ours. Instead, we tend to find a lot of solar systems where the planets are much, much closer to the sun. Well, because they orbit faster and they're easier to find. So we're not so sure whether our solar system is particularly unique, or if we've got a bias towards how we observe other solar systems. But just from looking around our neighborhood of the galaxy, within a few thousand light years of the sun, we've taken a survey of stars and measured planetary systems. And it seems like 70 to 80% of star systems have planets orbiting them. So planetary systems are absolutely ubiquitous within our galaxy, or at least within our belt of the galaxy. And there's lots of galaxies out there, right? So something like 100 billion galaxies like the Milky Way in our observable universe. So probably lots and lots and lots of planetary systems out there.
But how far into our own galaxy can we see with enough definition to be able to identify solar systems?
Right. So our Milky Way is about 100,000 light years across. So it takes light about 100,000 years to make it from one side of the galaxy to the other. And with any kind of confidence, we really can't measure planets outside of about 1,000 light years. So about 1% of our galaxy, right? There are some other methods that we use to find planets, gravitational microlensing and stuff like that. And we have found planets even orbiting a quasar outside of our sorry, not a quasar, a pulsar, far away from the sun in our galaxy. And so we have found some of these things, but the majority of planets that we talk about, they're all being found relatively nearby in our sort of region of the galaxy, in what we call the solar neighborhood. Yeah.
One last question from me.
Uh-huh.
We refer to a Mars-sized object impacting the Earth and creating the moon.
Uh-huh.
Or gravity?
Yeah. Well, no, it became the part of the Earth and part of the moon, right? So when we look at the moon and the Earth, unlike looking at, say, different comets or Saturn's moons and comparing those to the Earth, the isotopes, the number of, for example, hydrogen atoms with 1 neutron or with 2 neutrons, which we call deuterium, the number of those, the fraction of those, are the same in the Earth and the Moon. So the Earth and the Moon on the surface have similar compositions. The Earth and the Moon have very, very different metal cores, right? The Earth's metal core is much, much more pronounced than the Moon's metal core. And the Moon's metal core is small on the scale of the other terrestrial planets. So what we think happened is you've got this newly formed Earth. At that time, it wasn't much more than a lava lake anyways. There was still the surface was too hot to have cooled and solidified. In the early solar system history, this Mars-sized object, which was similar, hit the Earth, but just a little off axis. And so it gouged out, it destroyed itself completely, gouged out a big chunk of the Earth's mantle, and all that debris went into orbit around the Earth. It formed some rings which coalesced into 2 moons, one of which went and impacted the Earth again, became part of the Earth. So the moon was completely, except for its core, completely destroyed in this event. And so Theia and the Earth sort of merged to form the Earth and the moon, right? And there's no leftovers of Theia.
No leftovers.
Right.
You're dealing with a very large system. Is it necessary to take dark matter, which we know little about, into your calculations at all? Or do you just assume that that's not there? How do you handle dark matter?
Right. So within our solar system, we can ignore it. As far as we know, we can ignore it. When we look at the orbits of the other stars in the galaxy, we can kind of put together a mass model of the galaxy. And it seems that even though dark matter should exist in the region of the galaxy where the sun and the Earth are, that material is sort of smoothly distributed within our region of the galaxy, so we don't have to care about its effects, because there's just as much of it in one place as there is in another. There's a new paper that just came out that I think is pretty interesting about what's called a dark matter subhalo. that talks about a region in our galaxy where there might be an overdensity, and we might actually see where there might be some dark matter that we can study that in more particular detail. But that's so far away from us that we don't have to care for our solar system. We can ignore it. Yeah.
Well, thank you so much, Dr. Jerousek.
Thank you. It's a pleasure to be here.
And thank you, everybody, for coming.